Okay, let's finish up chapter 7. We're going to continue graphing the trig functions. Today we're going to do the functions that have asymptotes. That would be tangent and cotangent, secant and cosecant. So let's get started with the tangent function. First off, let's remember that tangent, by definition, is sine over cosine. And that introduces something that we haven't been doing with the trig functions yet, and that introduces vertical asymptotes. So let's talk about them here. The vertical asymptote happens when the denominator is equal to 0. So where is the cosine of theta equal to 0? That's really our question, okay? And we know from the work we've already done getting to this point that cosine is equal to 0 at pi over 2. In fact, it's equal to 0 at all the odd multiples of pi over 2, okay? So the vertical asymptotes here are going to occur at the odd multiples of pi over 2. And I'm going to write that mathematically again, getting you used to this kind of notation, where k is an element of the integers. All right, so what does that mean here specifically? Specifically, our VAs for one period of the tangent function are going to be x is equal to negative pi over 2 and x is equal to pi over 2. These are the regular ones. We generally, when we're going to graph something, we often want to show the origin, right? And so in most cases, we graph that first period of tangent between negative pi over 2 and pi over 2 and then continue up the x-axis in the positive direction to do the second period, third period, and so forth. Excuse me. So let me draw in our vertical asymptotes here. So I've sketched in the vertical asymptotes, and now let me draw one period of the graph. And remember, with asymptotes, what happens is the graph gets closer and closer and closer, never ever crossing vertical asymptotes, never ever crossing a vertical asymptote. Okay, so it goes on forever. Let me throw some values in here. Here are our asymptotes. Our negative pi over 2 is here, and our pi over 2 is here. Okay, now let's get some other details here. So what's the domain of the trig function? The domain of the trig function is all real numbers except for all those vertical asymptotes. So we can write it kind of in set notation. I'll write like this: union with negative 3 pi over 2 to negative pi over 2, union negative pi over 2 to pi over 2. See if I can get one more in here. Pi over 2 to 3 pi over 2, going on continuously. Okay, so that's the domain. Let's look at the range. Now, I had told you in an earlier lecture that I would explain more why the range is all real numbers when the range for all the other functions are much different, and why the period here is pi and not 2 pi. So if you look here at the graph, remember when you first started learning about range and domain, you learned how to kind of read it off the graph. And when you look for a range, you kind of start at the bottom and you look up to the top, right? And if we're starting at the bottom, we see an arrowhead pointing down, and an arrowhead pointing down means negative infinity. And the last thing we see as we scan up the graph is another arrowhead pointing up, so that points to positive infinity. So the range is negative infinity to positive infinity. Now, the period of a graph, or the period of a trig function, is how far you have to go to encapsulate every single possible value for that function, okay? And for sine and cosine, because of the shape, it takes 2 pi units for you to get every single x and y value possible for the graph, for the function. Now, if you look right here at our graph, you can see that this has all the y values. And a period has to have all the y values. And this is all the y values. And the distance between pi and negative pi over 2 is actually pi, but you can check it. So you do want to check your period here. So let me write what the period is for the tangent function, and that is just pi, and it's pi because every y value can be put in the distance of pi. Okay, but let's look at how to check the period. We want to find the distance between these two. So we're going to say pi over 2 minus negative pi over 2, and that is equal to pi. So we've got it. Okay, so what other things do we need to talk about here? Well, we need to talk about x-intercepts. Remember, with rational functions, the denominator gives us the vertical asymptote and the numerator gives us the x-intercepts. So where is sine equal to 0? Sine is equal to 0 at all multiples of pi. So our x-intercepts here are going to be k pi, comma 0, where k is an element of the integer. The y-intercept is clearly, as you look here, 0, 0. Remember, you can have multiple x-intercepts but only one y-intercept. That is actually the definition of something being a function. For every input, there is only one output. In other words, for every x value, there can only be mapped to one y value. So you will only ever have one y-intercept on any function, no matter what kind it is. Okay, so what we've done here is we've graphed one graph. And let's see, anything I missed off my notes? Oh, yeah, one last thing that I mentioned about the other ones that I have not mentioned about this one is that this is symmetric about the origin. This is an odd function. And it means that it's symmetric about the origin. Okay, so and let me tell you, these asymptotes are going to become the key point on how to graph these kinds of functions. All of these 4 functions really depend heavily on understanding the asymptotes and how to manipulate them. Let's take a look at the cotangent function, and of course the cotangent function, cotan theta, is equal to the cosine theta over the sine theta. So that means that our vertical asymptotes happen when sine of theta is equal to 0, and we just talked about that sine of theta is equal to 0 at k pi, where k is an element of the integers. All right, so specifically our vertical asymptotes here are going to be, I'm going to use 0 and I'm going to use pi. All right, now anytime you have an asymptote that it happens to be on an axis, I just kind of do it with a little bit of a slant, just so it stands out and you can see it. That's just what I do. And then here's another. Now, cotangent is the cofunction of tangent, which means that all of its values are kind of flipped over. So the graph of the cotangent, instead of starting down and going up like tangent does, it starts up and it goes down. Now I always go in the center, so I have a starting point here. So we're going to be going up on the left and down on the right. All right, so let me put in our values here. Here is 0 and here is pi. Well, let's get some of our information here. The domain here of the cotangent function is all real numbers except for all of the even powers, or not even, sorry, all of the multiples of pi. So we'll just get us a little one here. So -2 pi, comma, negative pi, union negative pi, comma, 0. Don't forget, 0 is a multiple of pi. 0 to pi. Oh, that should be a union. Not that. Union pi to 2 pi, dot, dot, dot. Keeps on going. Great. How about the range? Well, the range is just like tangent, and notice all the values of y are in between that one little section there. So the range here is -infinity to +infinity. The period is pi, again for the same reason, and you could check this and you would need to pi minus 0 equals pi, check, because if there was any kind of phase shifts affect the asymptotes. So that's how phase shifts fit in here. What else do I need? I need x-intercepts. And remember, the x-intercepts occur when the numerator is equal to 0, and so that is going to be 2k minus 1 pi over 2, comma 0, where k is an element of the integers. That's all those odd multiples of pi over 2. Notice that this spot right here is pi over 2. And then, of course, the y-intercept. There is none. There is none because the x is equal to 0 is a vertical asymptote. I bet you haven't come across very many graphs in your mathematics career thus far that had no y-intercept, but here it is. If that vertical asymptote is at 0, you will have no y-intercept. Okay, let's look at the cosecant function. Let's see, and by definition, the cosecant of theta is equal to 1 over sine theta. So here we are. We've got a vertical asymptote situation. The vertical asymptote happens when sine theta is equal to 0, and so our vertical asymptotes occur at k pi, where k is an element of the integers. And actually, I should be a little more specific here. Let me be a little bit more careful. The vertical asymptotes are actually x is equal to k pi, where k is an element of the integers. Okay, so there's our vertical asymptote. So let's go ahead and draw that in. So we're going to have 0, we're going to have pi, and because the period of the cosecant function is 2 pi, we'll also have 1 at 2 pi. And let me draw this in for you so you can check it out, and then I'll write in all the other information. Oh, that's so terrible. I want it to at least look halfway decent for your... There we go. Okay, and let me put in our values here. This is 0, this is pi, this is 2 pi. So notice that our vertical asymptotes are placed at half the value of what the actual period turns out to be. Remember, your periods can change depending on omega, so I'm just kind of putting this thought in your head about it. Okay, so this is what we've got. Let's hit up our information here. So our domain is the same as the domain of the cotangent because sine is in the denominator. I'm going to go ahead and write this in set notation such that x is not equal to k pi, k element of the integers. Okay, our range. Now remember, this had a kind of a weird range, but let's just read it like we were in algebra class, okay? So we start from the bottom. Let me put some values in here because I haven't yet. Starting from the bottom, we go from negative infinity to negative 1, and it actually includes union, picking up again right here at 1. And the last thing we see are arrowheads, so it's an infinity. The period is 2 pi. And let's look at the picture. Notice it takes 2 pi units for us to get all the positive values and all the negative values for that function. And that is why the period is 2 pi. Also, if you were dealing with a phase shift or something like that, you would use that knowledge of that period to get them set correctly. Okay? You figured out what your asymptotes are and you check it, you got 1, say you're graphing 2 periods, you just add that value of the period onto that last asymptote and then take half of it, you'll get the middle. I mean, it just really turns into the fact that you know how these graphs behave, therefore you can put in all the details after you've drawn the graph, just like with sine and cosine. We know what they look like, we draw them, and then we put in the details depending on what the problem provides for us. Okay, let's see what's the next thing we need to hit up. Our x-intercepts. Remember, x-intercepts come from the numerator of our rational function, and that just says 1. There are no x-intercepts. There's none, and you can tell by looking at the graph. Remember, an x-intercept occurs when the graph crosses the x-axis. And then here, for a y-intercept, again, we're in the situation that there is no y-intercept because we cannot cross that graph. Okay, makes sense? Now, as a side note, and this is something very, very interesting to note, and I'm going to do this in another color. Okay, so one of the really cool things about the cosecant function is that it fits the sine function completely. You see that? So I've just dotted in a sine function, and you can see where the cosecant places and goes up. Okay? Just another kind of visual to kind of help you with this. All right, let's hit up the secant then. It's going to be basically the same thing. What's going to be different? The vertical asymptotes are going to be different. The vertical asymptote is not going to be on the x-axis, on the y-axis, so that means that we're going to have at least a y-intercept. So let's take a look. Okay, so remind ourselves up here that secant theta is equal to 1 over cosine theta. This is an even function, right? Because cosine is even. Just reminding you of some of these many things that we've been learning over the last 3 lectures. So the vertical asymptote happens when cosine of theta is equal to 0. And we've done this enough already this lecture. So I'm going to write it here. X is equal to 2k minus 1 pi over 2, where k is an element of the integers. Okay, and so that's going to tell us that we're going to have, in this case, I'm going to start with negative pi over 2. Then we've got pi over 2. And what would be the next one? 3 pi over 2. We're going to have a full period. So let's check. Why do I need 3 there? So I want to look. 3 pi over 2 minus a negative pi over 2 gives us 4 pi over 2, which is 2 pi. And our period needs to be 2 pi. So that confirms that we need to have 3 asymptotes for 1 period. Okay, so let me put this guy here, this guy here, and this guy here. And let me draw this one. Oh, let me draw better. I'm sure you can imagine at this point, you know, that this is happening at, this is like 1, and this is going to be negative 1. All right, and let's get some of our info here. Our domain. The domain is all real numbers such that x is not equal to the odd multiples of pi over 2. The range. The range is the same as the secant for the same reason. We start at negative infinity and we stop at negative 1, and then we pick up again at positive 1 and we go to infinity. The period. The period is 2 pi and it's 2 pi because it takes that much for it to show all of the positive and all of the negative possible values of the secant function. And now let's look at x-intercepts. X-intercepts happen when the numerator is equal to 0. There's none. The graph does not cross the x-axis unless there was some kind of crazy vertical shift or something like that. Okay, and then the y-axis and the y-intercept, well, unless there is an amplitude, the y-intercept is always going to be 0 and 1. Okay, cool. So I'm going to graph 2 periods of this given equation. Okay, so what are the things that we need to look out for? We need to know, do we have an amplitude? Which, by the way, amplitude does not affect the tangent function because it's still going to be negative infinity to positive infinity, and because we're not getting into the weeds on the details, your sketches are going to look exactly the same. And then we need to know our period, and our period is pi over 1/4, which is equal to 4 pi. All right, now we need 2 periods to graph because that's what I asked for, 2 periods. So we need to do a little bit of work on getting 2 periods. So 2 periods means that we're going to have to go out, be a total of 8 pi. All right, so probably the easiest way for me to do it is let's just draw it and then put in our numbers. Let's do that. That's usually how I do this without thinking it through beforehand. So let me just draw in 2 periods. All right, now we can't just say that this is 8 pi here because it's 2 periods, because what we have to figure is that this range right here has to equal 4 pi. So what do the values need to be there? Well, I say that this needs to be 2 pi and negative 2 pi, because 2 pi plus negative 2 pi, 2 pi minus negative 2 pi is 4 pi. Okay, that's what we need in tangent 1 period. So let me just draw in my graph real quick. I'm good with it. So if this has to be a total of 2 pi, I mean 4 pi, goodness gracious, this should be then 6 pi. This guy in here. It's kind of like working out a puzzle, right? Let's figure out these middle points. Well, let's make sure that this whole thing is right. 6 pi minus a negative 2 pi equals 8 pi. That's cool because we needed 2 times the 4 pi. We needed a total of 8 pi area. So there's our 2 periods. The amplitude was 1, our period was 5, and let's get 5 points here. So let's figure out what these little middle points are. This is 0, right? And then this is going to be 4 pi. That hits all the important ones. You could probably, just from this, we could set some patterns. We could say something like, the vertical asymptotes happen at, let's see, 2, 4, 6, 8. The next one will be 10. Looks like it's going to be 2 pi, 6 pi, add 4. Next one's going to be 10 pi, add 4, 14 pi. So we could come up with a way to say that, but I guess I'm going to not get in the weeds here. I'm going to leave that for your Calculus 2 class. But this could talk about how they go on, right? You could get an idea of what that pattern is. And then the same thing for those x-intercepts. I just like to write this kind of stuff down just because it helps me kind of think them through later. But that looks like starting dot, dot, dot. Looks like we could do negative 4 pi, and then 0, and then 4 pi, and then 8 pi, and so forth. That would be all the x-intercepts. I'm not saying that you have to do all that. I'm just saying that it's good for you to know how to do all of that, because you don't know what you're going to be asked to actually do in the classes beyond this. And this class is preparing you mathematically for the classes beyond this, okay? All right. Let's do the cosecant. That's 1 over sine. Let's get all the info here. Let's see. We have an amplitude of 1. I'm not trying to be all too hard here. Let's look at our period. Our period is 2 pi divided by 4. So our period is pi over 2. And we need 2 periods. So 2 periods means that it's going to be pi. Cosecant is 1 over sine. And where is sine 0? Sine is 0 at all the multiples of pi. So our vertical asymptote here are going to be x is equal to 0, x is equal to pi, and x is equal to 2 pi. That's 1 period, and then the next period is going to be 3 pi, 4 pi, 5 pi. What am I doing? I think I lost my mind. Y'all ignore all of that. Just ignore all that. Just ignore it. I mean, it is true, but just ignore it here. Let's just go ahead and draw this in and do it the way that I always do them. I don't know what my problem is. Okay, so let's just draw the picture. And then we'll put in our values. I don't know why I'm trying to figure out the values first. I never do it like that. Okay, but I do know that they're going to happen on the pi's. So let me just... Okay, and let me just draw in my graphs here. We're doing cosecant, so that looks like an omega, doesn't it? It's okay. Let's just get it done. Okay, so this is 1 period. There's that second period. Okay, and at the end of the second period, it should be equal to pi. So let's do it like we did it with the sine and the cosines, okay? If that's pi, then this is pi over 2. If that's pi over 2 and that's 0, then this is pi over 4. If that's pi over 2 and that's pi, this is 3 pi over 4. And then let's find these middle values just for giggles here, like this one right here. That's pi over 8. And remember how we did it with the signs. It's 1 pi over 8. 2 pi over 8 is equal to 1/4. So this will be 3 pi over 8. That's 4 pi over 8, which is pi over 2. This is 5 pi over 8. 6 pi over 8. 7 pi over 8. So we don't have to do any real math. We just have to understand the pattern and understand how to count it up. So there it is. And we've indicated plenty of points on the x-axis. Okay. We have one left, and I know I haven't given you any u-dos this time, but I'm not going to. I want to go ahead and do one more example of each of these guys. So I'm going to do this one and let you off the hook for the u-dos. Be ready to start Chapter 8 and all the u-dos for you. Now, let's talk about this one real quick and finish this guy up. We have an amplitude of 1. Our period is equal to 2 pi divided by 2. So our period is pi. So we're going to need a total of 2 pi. Let's go ahead and start drawing it up. So secant is 1 over cosine. I think I might have to extend my business out here. Yeah, let me extend it out just a little bit. The world's most crooked line. That's all right though. And let me draw them in. Now, if the coefficient of this was negative, we would start down here, right? It'd just flip everything over. So and I kind of feel like secant might be one of the harder ones to do. Let me show you a little trick that I sometimes do for secant so that I don't have to think quite as hard. I go ahead and put one more. But it's just half of the graph. So basically, instead of starting over here, I just take that extra piece and lump it on the end right here. Now, why do I do that? I do that because now I know that this spot right here is 2 pi. Because that's a full, check it out, you'll have to look at it like this. Let me mark it from here. So here to here is 1 period. So in fact, that would be pi. And from here to here is another period. And each period needed to equal pi. So that's a way to get around having to do all that extra work. Other than that, we could have figured out the extra work because we knew that this was negative pi over 2. And so that's pi over 2, 3 pi over 2, 5 pi over 2. That's 7 pi over 2. And we could check that is 7 pi over 2 minus a negative pi over 2. That's 8 pi over 2, which is 4 pi. And that's too much. Darn it. Well, what did I do wrong there? No, that's right. I just don't know. I think this is something's wrong with these numbers. Let me go ahead and erase these and figure it out the usual way. Kill that. Let's go ahead and do what's in between pi and 2 pi, and that is 3 pi over 2. What's between pi and 0? That is pi over 2. What's between pi over 2 and 0? And this guy would be pi over 4. And so now we have pi over 1 pi over 4, 2 pi over 4. This would be 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, and 7 pi over 4. Well, I had that right. I don't know why. Because that should have actually been negative pi over 4 because of the period shrink, not pi over 2. Ah, darn it. Okay. As you see, it does require some work. You do have to mess around, but this would have worked anyway, okay, once you figured out that number. But this is a trick. This is a good trick when you're dealing with secant. It's just to avoid this piece right here, and it makes it pretty quick and easy. All right. Have a good day.